Good morning once again.
Good morning, sir.
Okay, well done. Sorry for that delay. We just had to wait a little more time for others to join. But I think we can kick off for now. Okay.
Okay, good morning.
Yeah, good morning. Welcome. We want to continue from where we stopped last time. Today we want to look at radiation from electron transition. When photons or particles interact with matter.
Good morning, sir.
Yeah, good morning.
It's Francis.
When photons interact with a matter, you can either have a photon coming, you can even be photon or any particle coming. You can interact with orbital electrons or move down into the nucleus. So those are the two main ways, in fact, the two ways in which we can have interaction with orbital electrons or interactions with the nucleus. So today we want to look at radiation from electron transition. For now. When we have radiation, or say we have a particle or electromagnetic radiation interacting with an atom, you have that electron. Okay, we're looking at electron now. We have that electron to have received an amount of radiation, an amount of energy. It becomes excited. And when it becomes excited, we all know nature abhors instability. When it has become unstable, the next thing it does is for it to release the energy. And the energy it releases has to be either in form of characteristic radiation or other electrons. You have an atom that has received energy which has impacted the electrons, that is the orbital electrons. Because when they receive such energy, they become excited. In that case, for them to be to go back to their lower energy state, that is to become stable again, they have to release either characteristic radiation or other electrons. How do I mean? You have an electron, you have an atom, so many shells. You have energy coming maybe by way of one photon, X-ray, or particles. It could be charged particles like a proton, positron, and so on and so forth. It interacts with this, with one electron here. A characteristic radiation mainly refers to a transition from maybe one shell to the other, assuming this one receives an amount of energy. It becomes excited. It has more energy now. All it has to do is it goes down to this. It goes down to this particular energy level because it can no longer be accommodated here. When it goes down here, the energy, the excess energy because it has a particular binding energy, the energy holding it to this nucleus so that it continues to revolve in space. With that in place, when it goes down here, the excess energy has to be released in form of either light waves, light rays, ultraviolet radiation, or when the energy exceeds 100 electron volts, then we have a characteristic X-rays. I mentioned it last time. I just want to be brief about it. So when the energy of the transiting electrons, that is the energy of the transiting electrons, the energy between here and here exceeds 100 electron volt, then we are talking about a characteristic X-ray. And we call it characteristic because it is a characteristic of a particular atom. Assuming this is a K shell, KL, M. For sodium, it has its own, when there is a transition from L to K, it has a particular energy range, characteristic of sodium. When it is calcium and so on and so forth. So that is why the name characteristic was coined in. At times, the transition might not give us a characteristic radiation, the transition from one shell to the other, because of energy that has been absorbed by the electron. The transition can be in such a way that the energy that has been released in form of this X-ray will just be taken up by another electron in that cascading shell. You have electron moving from here to here, and the giving rise to electromagnetic rays. We are particular about this. The energy might be given to another electron. Another electron can absorb that energy and become ejected. That electron that has become ejected is called Auger electrons. So these two processes, they compete during photon interactions. We're going to see some of them. Are we talking about especially photoelectric effect, pair production, and so on and so forth? They all compete for relevance during all these interactions. So this is just a little brief about it. A recap of the last part of our lecture last time. So let's quickly go, because there's so much to cover in this topic, and I do believe we wouldn't be able to do the justice to all of them today. We might have to fix one more lecture to cover it comprehensively. So I want to look at atomic nucleus now. Atomic nucleus. Of course, we know the composition of a nucleus. Protons plus neutrons. All nuclides, all elements have protons and neutrons, just except hydrogen. The first isotope of hydrogen, protium, which doesn't have a neutron. No neutron. So apart from this one, every other element, every other nuclide has a neutron. So for example, hydrogen and protium has a 1 neutron, 1 proton, tritium has a 2, and so on and so forth. So all elements, all nuclides actually have protons and neutrons, and this is what constitutes the mass number, Z of proton plus a neutron. Constitute, Z is the proton number, constitutes the mass number of an atom. So whenever we see this inscription, we have element X, we have something here, the mass number. The number here is the proton number, usually written this way. And in some textbook, you might have the symbol, take the shape. Let's say iodine. 131. It's a 3. So this one denotes the proton number Z, whereas this one denotes the mass number. To get a proton number from mass number, you simply do this small arithmetic to get the number of protons in an atom. We are not just doing this mathematics for the fun of it, and we are doing it because it is going to lead us to the nuclear force that exists. The nuclear force that exists inside the nucleus, different from the Coulombic force, which holds that the nuclear force is inside the nucleus. It is a very short range, very, very strong force that holds the constituent of the nucleus together, that's the proton and the neutron. Very, very strong attractive force, different from this Coulombic repulsion between electrons. So it says a lot about atoms, whether an atom is going to be stable and so on and so forth. So we have this nuclear force holding proton and neutron together, proton and proton together, and even neutron and neutron together. We have a neutron nuclear force. You have a neutron, proton nuclear force, and also proton and neutron nuclear force. We wouldn't go into the semantics of this, just for us to know that these forces exist. And this one is related to Coulombic force. Whenever we see Coulombic force, it has to do with either attraction or repulsion. Likewise, we also have a Coulombic force among electrons, between electrons and among electrons. Here also we have a Coulombic force among a proton. Of course, this is a neutron-neutron, it is not charged, so there is no Coulombic force existing between here. All these forces, nuclear force, Coulombic force, and blah, 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 proton-neutron force, they are what constitute the net nuclear force we have inside the nucleus. And the force, like I said before, very, very strong. It is different from the Coulombic force holding the electrons together. Those ones are very minimal. So at times when we want to calculate the binding energy of an atom, the some atom, most times we neglect that of the electron binding energy because very, very insignificant when we want to compare it with the forces originating in the nucleus. We have so many classifications based on combinations of protons, neutrons, and so on. You could have like iodine. We have iodine 131. I mean, you also have iodine 125. These are different nuclides. Of course, the same elements, iodine. They have a different number of, they have the same number of protons, they have the same number of electrons. Of course, for an atom to be electrically neutral, the number of protons should be equal to the number of electrons. This one has the same number of protons, but they have different number of neutrons. So their mass numbers are different. They have a name for that. And at times, you can have nuclides with the same proton number. You can have nuclides with the same proton number. Let's say, for example, hydrogen. Hydrogen has about 3. We have a protium. We have another one, maybe another proton, another hydrogen called the deuterium, and so on. And the other one, hydrogen 3, is 2, this one, tritium. They all have the same proton number, but a different mass number. Also the same thing with this classification. We could have nuclides in which they have the same mass number and the same A, and the same proton number. For example, one of the most used or the most sought after radionuclide used in nuclear medicine as our technetium 99N. It has the same number of A and the same number of proton. So which it has a special name. I don't want to mention the name. I have a diagram in which we have a very clear distinction between the nuclei we are going to be encountering throughout this course. So based on that, we could have protons, we could have a nuclei that have the same mass number, but different combinations of other nuclear elements and subatomic particles. We could have the ones that have the same proton number, but different combinations of the other subnuclear particles, and so on and so forth. Let me just share. I want to share a screen with us. Share the screen. Okay. I hope you can see the screen.
Yes, sir.
Okay.
Yes, I can see.
Okay. Thanks. So we have so many families of nuclei. And the first one here, atomic number, they have the same atomic number, like the one I mentioned here, iodine 131 and iodine 125. The proton number is 53. They have the same atomic number. So we have a special name for them, isotope. Of course, this is a name we've been using right from our days in the secondary school. Isotope. They have the same number of protons on different number of neutrons. Of course, because they have different number of neutrons, it means they have different atomic mass number. Then for these isobars, they have the same number of they have the same mass number, A, but different neutron number. They have the same mass number. They have the same mass number. They could have some combination. They could have a different proton number and so on and so forth. But the emphasis is on the same number of proton and neutron, the same combination of proton and neutron. That is this one is the 99. Technetium 99 is also 99. Molybdenum. Molybdenum happens to be the parent of technetium 99. During production of technetium 99, which is the most used radiopharmaceutical agent in nuclear medicine. During the production, we have we milk technetium 99 from molybdenum parent. So this is daughter and this is it. So they essentially have the same mass number, 99. The next family we have here is the isotones. This one have the same number of neutrons. Like you have iodine 131 here. This one has 78 neutrons, whereas this one has this one also equally has 78 neutrons. So the name coined in here is isotones. If you look at these first three, at times they're usually a mix-up. We might mix up these names, isotopes, isobars. But for clarity's sake, this P here, this A here, and this N here, they are the key to we understanding or we communicating to heart. I think the P here denotes the same number of protons. The A here denotes the same number of mass, that is A. The same number of A, that's the mass number. And the N here denotes the same number of neutrons. So with that, there shouldn't be any mix-up whenever we come across questions that have got to do with distinction into the different nuclides we encounter in medicine, in physics, and so on. And for the last one here, isomers, the one I talked about, technetium 99M, technetium 99, has they have the same number of everything. They have the same atomic number, the same mass number. Of course, that tells us they have everything in common. But it is just because of their different energy states. They have a different energy. One is more energetic than the other. This technetium 99M is more energetic than technetium 99. And when we come to nuclear medicine, we see that the energy between them is of the order of about 142 kiloelectron volt. So if this one excites, if this one decays via isomerism, it is going to give us a technetium 99 with a photon of energy 142 kiloelectron volt. We talk more on that when we get to nuclear medicine. So let's continue with our lecture. So that brings us to nuclear stability. Nuclear force takes us straight down to nuclear stability. Nuclear stability. How do we distinguish which nuclide is going to be stable and which one is not going to be stable? Why is technetium 99M not stable, whereas technetium 99 is stable? Well, this is not a very good example. It's not a very good example. Why is uranium 235 unstable, whereas lead 82 is stable? The major key that tells us which nuclide is going to be stable and which one is not going to be stable is the NZ-NP ratio, neutron NZ, of course, I'm correct. Neutron proton ratio. Wanted to use N over P, which is the same thing. Z represents a proton. So the neutron proton ratio of any atom is going to tell us whether the atom is going to be stable or not. And why do we say that? There has to be a particular ratio that must be maintained for a particle or a nuclide to be stable. For low elements, those from 1, 2, 3, 20, and so on, very light elements, the NZ ratio should be equal to 1. That is, if you draw a graph of neutron and proton, if you have 10 here, you say 10, you have 10 here. Okay. So if you have 10 here, you also should have 10 protons for the mass and for that nuclide to be stable. But as this thing continues, as the number of the nuclear components begin to increase, this ratio no longer becomes untenable. Something has to happen to this ratio, because this neutron-proton ratio, they constitute the nuclear force, and the nuclear force has to be counterbalanced by the Coulombic force, which arises from the proton-proton interaction. So when that number of protons becomes so much that the neutron can't handle it again, the material becomes unstable. So for very high elements, from 82, from lead is the point where we begin to have unstable nuclides. Oh, we have to have nuclides. We have to have nuclides that have this ratio greater than or equal to 1.5. So we should have more number of neutrons than protons, so that if you divide the two of them, you should have 1.5 and the rest. So if you don't have that ratio, the material will continue to become unstable. So we are not going to go into the details here. When we come to nuclear medicine, we will dwell much more on this phenomenon of instability. But then the syllabus expects us to know at this point some of these terms and then the reaction that occur as a result of instability that happens in the nucleus. So we have the unstable nuclide, and the unstable nucleus, of course, becomes agitated. It's not comfortable. It has to emit the radiation. I mean, it has to emit the excess energy that it has in form of a radiation. And how does that happen? It happens via so many processes. And that atom that has become unstable is said to undergo radioactivity. Radioactivity. It has to undergo radioactivity for it to become stable. Radioactivity is simply the disintegration of, let me not use that word. Radioactivity is the giving off of a radiation in an atom, in a nucleus, for that nucleus to become unstable. So there are so many processes. There are so many processes that could take place for that atom to become stable. One of them is, of course, in our basic physics in secondary school, we can identify three radiation in radioactivity: alpha ray, beta ray, and gamma ray. It actually still holds. These three distinctions actually still hold, but much more than that. Radioactivity is treated under these processes in which the atom becomes stable again. The atom can become stable via beta plus, let me start with beta minus emission. Can have a beta plus emission. We can have alpha emission. We can have an electron capture. We can also have so that one in form of isomerism or gamma ray emission. Gamma rays emission. Through these five major processes, the nuclide now becomes unstable. Whether it's going to be this emission or this emission depends on the conversion of neutron to proton or proton to neutron. When this number becomes this n over z, it's not 1.5 and above for high z element, for higher mass element. Then either the proton is converted to neutron, either the neutron is converted to proton, or a proton is converted to neutron. Like I said, we are going to deal with this much more in a comprehensive manner when we get into nuclear medicine. Nuclear stability. In all these processes we have mentioned, the beta emission, beta particle emission, alpha, beta plus particle, beta minus electron capture, isomerism, and then alpha, blah, blah, blah. They actually take place via gamma, return to stability. Return to stability. It happens via gamma ray emission. Gamma ray emission or internal combustion. That is when we've gotten, when maybe an alpha ray has been emitted or a beta ray has been emitted, beta plus ray particle has been emitted, a beta negative particle has been emitted, and so on and so forth. For those first things, the material returns to becoming stable via gamma ray emission or by internal combustion process. Internal combustion process is the counterpart of Auger electrons. Auger electrons for electron transition. When the orbital electrons have become excited, they could either go through the path of characteristic emission or Auger electron emission. That also happens in the nucleus. For the nucleus to become stable, instead of the gamma ray, because it is essentially by the emission of a gamma ray inside the nucleus, for it to become stable, for the nucleus and to become stable again, either the gamma ray becomes emitted, or the gamma ray, as it is moving out, you have the nucleus. Gamma ray has been emitted, but in the close proximity of the orbital electron, the energy can be passed to an orbital electron. This energy of the gamma ray can be passed to an orbital electron, and it becomes ejected. So in that method, in that way, we have internal conversion. That is, the energy of the photon has been converted to that of an electron that has been ejected. It is just almost the same thing with what we dealt with Auger electron. I think this is just about it. We have so much more to do today. So many things to do today. So we might want to go and read them, but actually there's nothing so much to read. It's just for us to understand the what we are talking about. An atom that has become unstable has to go back to stability. All these things we are talking, they happen within a few seconds. At times 10 raised to the power minus 8 seconds. That is, in 1 second, a process would have taken place maybe 100 million times. Okay, 1,000, a billion, okay, just close to a billion times. So very, very, in a second, you should know what this is all about. Very, very minute. We can't decipher this time of duration with our eyes. It is impossible. So this is the range of, or at times, this internal conversion can take years. At least this return to stability, they can take years in some nuclides. There are some that can take up to 100 years for them to come back to stability, or even more than. Whereas some take just a fraction of a second, like encounter in nuclear medicine in technetium 99. The process takes very, very fast time, and that is why they are called metastable at times. Metastable. Their stability is the stability comes much more faster than that of other nuclides. So we now go to interactions of radiation with matter. In medical imaging, we are actually using radiation or it can be particle or electromagnetic radiation to affect a particular change. You want to look at the anatomy, you want to see if a particular organ is diseased, you want to see the physiologic processes happening in the body, you want to look at the rate at which blood is flowing, which might be an indicator for a diseased organ. You're looking at a fracture, you're looking at a vessel that has a rupture. All these things happen because of interactions of a radiation with matter. When these interactions occur, what happens? The matter, the body, of course, processes will take place via excitation, via. So we want to look at the interaction of radiation with matter. Interactions of radiation with matter. As in the light of this, we are going to look at the particle interaction. I'm going to look at the particle interactions and of course the other one, X-ray or gamma ray, X-ray and gamma ray interaction. For X-ray and gamma ray interactions, we X-ray radiography, CT, mammography, fluoroscopy, and the likes. Whereas for particle interaction, we are looking at the interactions of electrons, interactions of B plus particles, beta minus particle negation, positron. We're looking at the interactions of protons with matter, interactions of neutron with matter, interactions of alpha particles with matter. Because during when these two at times they can be interwoven. When an X-ray enters a material and enters matter and it interacts with maybe the orbital electrons. The orbital electrons as they traverse matter are going to cause a further disturbance or further ionization or further interaction. So at times they used to, in fact, most times they always go together. The X-ray that has been generated knocks off electrons and so on and so forth to give rise to particle interaction. But for now, we want to look at want to divide the interactions with of radiation with matter under these two headings: particle interaction and X-ray interactions. Of a particle interaction, a particle can interact with, you have a particle, we are looking at matter now, and the matter we are considering is the basic form, which is the atom. When we have a particle, it can either interact with the orbital electron or interact with the nucleus. And the interaction of a particle with orbital electron or with this stuff are going to give us different things. when the particle interacts with orbital electrons, of course, they're going to have like to excite the atom, and after excitation, the atom will go back to normal, or it can cause the atom to become ionized when the electron has been given up. So the particle interactions can be happening in the neighborhood of the orbital electron. Orbital electron is again going to give rise to some things, or it's going to be happening inside the nucleus. When the particle that is traveling and towards the atom escapes and doesn't interact with the neutron. I mean, it doesn't interact with the electron. Of course, we can have that. It is very, very possible. In fact, it happens so many times. So that the particle now goes beyond the shell of the atom and moves into the proximity of the nucleus. So for a particle interaction, for orbital electron interaction, it's a nucleus interaction. This can, when a particle interacts with the electrons in the orbit, it could either lead to excitation, or ionization. For excitation, something is excited just from the name. When somebody is intoxicated, and the person begins to act in a funny way. Of course, it happens, the person can become hyperactive. That happens with interaction with orbital electrons. You have a particle interacting with this. The particle can cause the electron here to have to become energetic. Of course, it imparts so much energy to it that it becomes, it mustn't be so much energy. It imparts an amount of energy into it and becomes excited. It gains energy. When it gains energy, it is no longer comfortable. This place that used to be its comfort zone is no longer its comfort zone. It wants to go somewhere else. And in doing that, it goes somewhere else. And in doing that, when it comes down here, energy is going to be released, and the energy that will be released is just the difference between this shell and this shell. And after that, what happens? The stuff can go back to its to its normal state. But in another, during other times, like in pumping, scattering, and in photoelectric emission, you're going to have the electron leave this shell, leave the atom. And when it leaves the atom, you now have an ion pair, the hole, this one which is called the hole, and the electron, this one which is positively charged. It will now become positively charged in the sense that it will now have a net positive charge. It's not as if we don't have electrons again. If one electron moves away from here, you have an energy, you have a particle which has an energy equal or greater to the binding energy of this electron. For excitation, the energy is not equal to the binding energy of this. The binding energy of the electron here is the energy holding this electron to this nucleus. But if that energy is not enough, if it acquires an energy such that it is the energy difference between here and here, it will jump from here and here. If the energy difference is such that it is much more that it can jump from here. If the energy difference between that for that with that incoming particle is the same thing as the energy difference between here and here, it will jump to here. It will just move straight down to here. From quantum mechanics, if the energy is not anywhere close to this, no matter the amount of energy this receives, nothing is going to happen. That's for excitation. But for ionization, we are looking at the complete detachment of electron from the shell. When that happens, the atom becomes charged, negatively, positively charged, while the electron that has left is, of course, a negatively charged. So ionization happens at very, and 70% of interaction that happen in soft tissue is as a result of um, deposition because of ionization. Whereas ionization is at a very low end, low energetic particles. They give rise to um, this mode of orbital electron energy, orbital electron interaction. If you have energy most times greater than 40 electron volts, then ionization is most likely going to occur. This electron volt, 1 kilo electron volts. But if you have around the 40 electron volts, these two can be 50-50. Interactions as a result of excitation and ionization, they might be the same thing. But when the energy is below 40 electron volt, it is not able, it is no longer it can no longer support the ionization energy, the binding energy of the electron. And then it can only excite it. Mind us, this excitation or ionization, it is different for different particles. For example, and what is going to cause maybe iodine maybe 131, 125. The energy to move from L to M is different from that in oxygen, moving from K to N. So also bear that in mind. This is just for soft tissue electron range. In soft tissue, this is just about the range. 40 electron volts is about the time in which the two contributions will be roughly the same thing. But if the energy is so low, below 40 electron volts, then this one predominates. Whereas for high electron energy, ionization predominates, because for soft tissue, the binding energy, we can use the word binding energy for soft tissue, just around the 11.2 electron volts, and so on. So this is that about orbital electron interaction. And when we go to nucleus interaction, in the event that the particle goes beyond the proton, beyond the wall of the atom and gets into the nucleus, you're going to have a nuclear interaction. Imagine an electron moving, which is a particle moving. This one is positively charged. This one is negatively charged. The nucleus is positively charged. If it can be such that as it is moving away, because this one is positively charged, it will tend to attract it closer to itself, because it is positively charged. Like below, like charges repel, and while a lack charges attract, because it is oppositely directed in terms of charge to this. The nuclear material want to attract it because of the presence of a proton there. So this sudden deceleration will cause, because of sudden deceleration, because energy has to be conserved, we now lead to the formation of a photon energy. A photon leads to the formation of a photon of X-ray, which is given the name Bremsstrahlung.
Sorry, sir. Hello, sir.
Okay.
Sorry, I didn't get that photon. The last the one about photon energy.
Okay, photon energy. Okay, I was talking about orbital energy, orbital electron interaction. That is, if a particle can, coming into an atom can either interact with orbital electrons or move towards the nucleus. Orbital electron, I said the two ways are via the electron interaction. After interacting with the atom, it could make the atom become excited, so excitation, or ionizes it, ionization. Except for ionization, it requires some higher energy. For soft tissue, it requires higher energy. And then for soft tissue, in which we, of course, be dealing with radiology, about 70% of all interaction is as a result of this. So as a result of deposition of energy by means of ionization. That is, the atom will become ionized. The tissue under discussion, we are, this is the tissue we are looking at. You have a particle entry. We have so many atoms, so many atoms which have their electrons and so on and so forth. So this one is because we have so many particles, billions of particles. This one will interact with this interaction. But in the long run, most of the interactions will cause ionization, and that is why we can actually use some equipment to measure ionization. We have an equipment called ionization chamber. It is just because we ionize an air. We ionize a portion of an air by using ionizing radiation. Then the charges collected can give us um, not a guess, will give us the amount of charge that has been deposited, kind of. So ionization is about 70% probable. It happens 70% of the time, as against excitation. Because excitation, because the energy we use in radiology, is much way greater than 40 electron volts. So, but at 40 electron volts, these two, they can be roughly the same thing. But above in this one, because we are not dealing with much more energy, they tend to ionize the atoms they come in contact with. So 70% of them at very, very high energy rate. This one now almost tends towards 0. So we're looking at nucleus interaction. Interaction with the nucleus. I said when a particle interacts with the nucleus, and most time charge the particle this time around. And this time we've been talking about charge the particle interaction, not uncharge the particle like neutron. Neutron, the interactions of neutron is very, very different from the interaction of charged particle. Every other particle we're dealing with all other particles are charged particles. So when a charged particle, like a proton, like electron, doesn't interact with its fellow orbital electrons, but has energy to go close to this, to the nucleus. Of course, this has to do with some particular amount of kinetic energy. So if you now move close to the proximity of this, what happens is if something becomes bent, because it is moving with speed, it now encounters the nuclear force of the nucleus, which is attractive and also attractive because of the presence of a proton. The proton will want to get it, but because of its kinetic energy, because of the energy it has, due to its motion, it will tend to bend. And then that deceleration, that application of the brake will appear as a form of a radiation called Bremsstrahlung radiation, and it is a type of X-ray. In fact, most of the energy, most of the X-ray energy we use in all X-ray applications, most of them is a result of long X-ray. It is different from a characteristic chemistry. Characteristic chemistry, in the sense that this X-ray originates from the nucleus, whereas this characteristic X-ray originates from the orbital electron. We're going to get more of this when we enter the next topic, which you have to do with X-ray production. So for now, just for us, it is enough for us to know that in nuclear interaction, we could have Bremsstrahlung, and at times you can even have internal conversion, in which this comes inside here, comes embedded, and gives rise to a material which is different from its original one. So that is I would say that is all about the particle interaction. That is just a little explanation about the particle interactions. But there are some terms in particle interactions that we have to know for us to, that will lead us into further subtopics, which of course is demanded by the syllabus. So particle interaction as charged and particle. Sorry, it's charged particle, not just a particle, because we are going to treat neutron interactions differently. So charged and particle, charged particle interaction terms. There are some terms that we need to understand, that we need to know, and we come to charged particle interaction. One of such is a specific ionization. You have a charged particle moving inside the matter. You have an electron moving inside matter. As it enters here, it is going to interact with orbital electrons and so on and so forth. It's going to interact with the nucleus and so on and so forth, and produce further charged particles. So specific ionization is actually the number of ion pair produced. Number of ion pairs produced per unit length. So we have a charged particle moving. As it is moving, it is causing harm. Of course, that is actually what is happening. It is causing harm, but that harm will be used for the benefit of imaging. If that harm is not caused, then we are not going to see anything. So that is why there has to be a play between patient safety and between image and quality. Image and quality and dose. The more the dose we give to a patient, the more the radiation dose we give, the better the image quality. But this comes at a price, dose and price. So we want to look at, we should be able to manage that those shouldn't be so much, so that becomes a detrimental to the patient, and then the image quality shouldn't be compromised. Because what's the need of reducing the dose, so that then one wouldn't be able to see anything. At the end of the day, the patient receives unnecessary dose without we having any diagnostic quality from the radiation that has been imparted. So specific ionization is just the number of ion produced by that charged particle per unit length, and it is directly proportional to the charge all over all over velocity squared. The more the charge, the more the number of charged particles we are going to have. So I can compare the charged particle of alpha 2 plus to the charged particle of electron. This one is going to have twice as much as the specific ionization that the electron is going to get. An electron is going to produce. So that is a very, very key. This is one of the distinctions between heavy charged particle and the light charged particle. The heavy charged particle have a bigger specific ionization as opposed to light charged particle. So from this, velocity, how does velocity come here? Velocity comes here because, for example, we can use a magnet. You have a magnet, you have a small magnet, you have a big magnet, you have an ion filing. And this one is going to attract more ion filing to itself than this. The mass of ion filings, this bigger magnet is going to attract towards itself will be greater than that, which this one can accommodate. And that has to do with the charge. The bigger the charge, the more the number of ion pairs that will be produced, the smaller. Then velocity, how does velocity come to play here? For okay, let's say this magnet is moving. You have the ion filings all around here, and this one is moving with a particular speed. Okay, we are dealing with speed now, so we use a tool how to. We're not looking at charge now. We are looking at specifically speed. So every other condition has to remain constant. So we have two magnets moving. This one is moving with maybe 10 meters per second. This one is moving with 100 meters per second through this place. What will be the effect on the number of ion filings captured by this and this? This one is moving slowly, and this one is moving very fast. I think it will interest us to know that this one will capture lesser ion filing because it is moving at a very fast rate. Very fast rate. Whereas this one that is moving slowly will have so much ion filings attracted towards itself because of its reduced speed. This one that is just fast can just move with minimal ion filing towards itself. So we just be scattered around the whereas just a few will link into it. So this specific ionization is an apt. This equation is apt in the sense that charge and squared over is directly proportional to the charge, whereas it is inversely proportional to the velocity. The more the velocity, the lesser the specific ionization. I think there should be a diagram you're going to see. Okay, so let me share this and then. I hope you can see the diagram. That's the diagram for specific ionization showing a particular peak. And can we see?
Yes, sir.
Okay.
Yes, you can.
So look at the diagram. This is the specific ionization. this computer. Okay. You can see the ion pairs per millimeter. Of course, it is measured, a specific ionization is measured in IP per millimeter. Number of ion pairs. When we say ion pairs, when an atom has been ionized, you have the positively charged nucleus or atom, and then the electron. This constitutes an ion pair. So this will actually make electricity flow because the potential has been created between one thing and the other. Electron potential has been created, so electricity can actually flow. So we have this. We have as the charged particle enters the vicinity, the proximity of the nucleus, it begins to travel slowly. As it is traveling slowly, it is interacting. It is interacting with the orbital electrons. As it is interacting with the orbital electron, it is kicking them out, producing ion pair. And as they are producing, the electrons that have been kicked out will continue producing other electrons, will continue producing other charged pairs. So it's something we just gradually be increasing up to a particular point in which we have so much more, so many charged particles. But something very important happens at the tail end of that charged particle. As it ends is maybe we are looking at 1 millimeter. At the end of its sojourn, the charged particle, maybe 1 millimeter, we just drop abruptly. Why? Because they will all expend their energy within that tissue and become zero. This is important, especially for radiotherapy. Very, very important for radiotherapy. That is why today in some advanced country, they are moving towards particle radiotherapy, in the sense that you are using a particle to treat a cancer. You can see from this diagram, because the ion pair has to tell us the damage that can be done to the body. Here we just have very little here. There wouldn't be so much damage because you just have very few particles that have been let loose inside the body, maybe electrons and alpha particles and so on. Till it gets here. So if you want to treat maybe 1 centimeter of tissue, you're looking at 1 centimeter of tissue now. No. This is the distance from the end. This is the distance from the end. So we should understand that distance from the end. And this is the distance from the end of the part of that charged particle. So when we're looking at this 7 here, this 7 here just tells us that with respect to where it is ending, it is 7 as it is going down here. So this is where it ends its journey. Well, that shouldn't give us a problem for now. So this Bragg, this peak is called Bragg ionization peak. It is important that we want the charged particle to deposit all its energy at a particular distance. Maybe we want to treat a cancer. We want to treat a cancer which is maybe 2 centimeters. Sorry, we have to want to treat a cancer which is 2 centimeters deep into the body. As we introduce the charged particle, we want it to deposit almost 100% of its energy, 100% inside that tissue. So that is used extensively in radiotherapy. We need to know these things because, of course, some of these things happen. They also happen in. That is why we can't use charged particles. We can't use some heavy charged particles like a proton for imaging or alpha 2 plus for medical imaging. Whereas we use electrons and gamma ray and so on, because we are going to have we don't need this. There is no need for us to have this Bragg ionization peak. So let's stop the share and continue. So that's about that specific ionization. We also have another term, a charged particle track. So we have a specific ionization one. We have a charged particle track. As a charged particle moves in a tissue of interest, it creates a path, and the path depends on whether the charged particle is heavily charged or not so heavily charged. If it is heavily charged, like a proton, like alpha, alpha particle, the charged particle track will be different from electron. Just imagine a sports car having a collision, maybe a side collision with a truck. We see the impact. Let's say this one is a truck. This one is a energy. This one is a sports car. Sports car. If these two, this truck and this ones have this one, if they have a kind of impact, the way this one is going to move up will be different from the way this one is going to move. But this one might just almost stay where it is without any movement. Whereas this one, depending on where, as we are talking about, maybe it can even be head-on collision or side collision. This one will just move up. If it is something like, if it is such that we can have elastic collision, when this one collides with this, it will just bounce off immediately, just bounce off. So that happens. That also can help us explain this charged particle track. If you have an electron moving through a body, it begins to undergo so many interactions. It comes here, interacts with this, move here, interact with this electron here, it can change this path, interact with another electron, bounce off, it comes scattered. So the path is going to be really tortuous. But for charged particle, for heavier particles, alpha ray, their path is not that tortuous. They tend to maintain a straight line path. So for charged particle like electron, they have the path length. The okay, okay. The path length and the range are very different. The path length is just the total distance it goes. All these distances, you can join them together. Whereas the range is just the effective distance. We started here. This is just the range. This is the range. This is where it started. It ended here. This is just the range. Range is just the penetration of that charged particle in matter. How deep is something has penetrated. Whereas the path length is the total distance that something has traversed. So you can see this and zigzag arrangement is just like a smoke particle dancing about in air, or very small particle of paper moving about in air. So it takes the path is really tortuous. It's different from a stone you drop. If you drop a piece of paper from air, from up, it begins to tilt and move from one direction to the other until it gets to the floor. Whereas if you drop a stone, it tends to move straight down because there is no air friction occurring with it. But for alpha ray, alpha particle, this path length and range, they're about the same thing. As it is moving, it undergoes very little scatter, partly. So that the path length for energetic particle is about the same thing as the range. This is one other distinction between an energetic particle and very heavily charged particle and light particles. And we also want to look at another a linear energy transfer. Okay. Let's look at another 24. Well, linear energy transfer. Linear energy. You can need to be fast now. Linear energy transfer, let. Let is just the energy deposited in the tissue as per unit length as a charged particle travels past it. And like before, it is very related to specific ionization. The light is directly proportional to Q squared. So for particles that have so much energy, so much charge, the length of them, their length, they're going to deposit so much energy, but it is inversely proportional to their energy. The more the energy, the lesser the length of the material. So high length materials are like the alpha particle, 2 it is a high length material, whereas electron and the photons, they are low length material. This one has got to do, it tells us a lot of things about biological damage. When the type of damage that an alpha ray will cause is much more than that which an electron will cause. So that is why we can easily stop an alpha ray with a piece of paper. Of course, just because of this, it doesn't travel so much, it comes down. But an electron, a photon can travel infinitely inside the tissue. So that is directly proportional to the energy, just because of the explanation we had here. Because energy is directly related to the speed of an object. So quickly, these are the 3 major things we need to know when we are dealing with a child and particle interaction. Then for radiative interaction, that is the interaction happening inside the nucleus. We have already talked about this radiative interaction, which is Bremser-Long in nature. I don't need to go into that again. Then we look at positron annihilation. We've been talking about mainly about electron, and so on and so forth. At times, the charged particle might be a positron. And this one is a very, very wonderful process that takes place, especially in nuclear medicine, when we are using PET scanner, positron emission tomography. A positron is just beta plus. When a beta plus is moving and encounters an electron, it becomes annihilated. Beta plus, like we did in our last lecture, I said that this and this, they are just essentially the same thing. Okay, this is a beta plus, and this is just I was talking about the beta minus and the electron. This one originates from the nucleus, whereas this one is orbital electron. So if you have this the antimatter of this beta plus as the particle we want to use, and it encounters this, what happens is the 2 of them, when they combine, they are destroyed, they are annihilated, and from there we have the production of a photon with energy 1.02 megaelectron volt. So this is a positron annihilation, and it is a byproduct of it just further explains this energy mc squared, relationship between energy and the mass. This mass becomes an energy. So we want to watch these things. So the neutron interaction, neutron. We are still talking about a particle interaction. And we haven't entered into the cross of the matter, which is gamma ray and beta, gamma, and then X-ray. So for neutron interaction, because a neutron is not charged, it's an uncharged particle. It takes it almost takes the grace of God for neutrons to undergo interactions with atoms. So special forces have to be applied. That is why the neutron, most times, it has to be so energetic. You have to fire with a higher velocity so that it can interact with the material. And then when we have a neutron interaction, we shouldn't spend much on this. A neutron doesn't interact with orbital electrons, but it can go down into the nucleus to interact with the nuclear material. It can either kick out a particular neutron from it and then takes its place, or become embedded there and then change the atom um, into another atom, because into another nucleus, except if the neutron here comes here and changes the proton into a neutron, or changes a new neutron, it can interact with another neutron here. And then that interaction brings about the change of that neutron into another proton. When that happens, this atom is no longer what it is. Assuming we have sodium. If a proton interacts with the nucleus of the sodium here and converts one neutron into a proton, this proton is no longer, this atom is no longer proton. Proton is 11. It becomes magnesium, matching into magnesium, element 12. So I think we'll do more of that when we get to radioactivity. When we are talking about nuclear fission that produces radioactivity. I think this should do for now. Let's move into a major topic. All these ones we have been doing so far, they are just precursors to gamma ray and X-ray interaction. X-ray and gamma interaction. X-ray, gamma ray interaction. We had earlier looked at particle radiation and particle interaction with matter. But now we want to look at the interaction of radiation with matter, and the radiation we are looking at X-ray and then gamma ray. This interaction is the key subject of a discussion when we are looking at the interaction in radiology, and then of course radiotherapy also. We have so many types of this, and so many gamma ray interactions, and how X-ray you can have something, you can have photoelectric, you can have air production, you can even have a photo disintegration, you can even have a triplet production. Triplet is just a particular type of air production. A photo disintegration will not talk about the in nuclear, in radiology, these are the major ones we are interested in. I'm not interested in photo integration, photo disintegration. Photo disintegration is just when you have the fire, maybe a charged particle, and it gets embedded inside the nucleus, and the nucleus just splits. The atom just splits with into some other fragments, very close to what we know in a nuclear fission. So we don't need that. Then for this one also, we have what we call triplet production, which we might just briefly look at. But these are the major ones, major production, I mean the major interactions of X-ray or gamma ray we encounter in a radiology, of course, and also in a radiotherapy. All this happen in radiology, in the radiodiagnostic energy range. They also happen in the radiotherapeutic energy range. But this the energy range placed by radiology makes us stop here and go beyond there. Of a radiotherapy and have total disintegration with all these ones that are happening alongside. So Rayleigh start there. Really. Rayleigh scattering, it is a type of interaction in which, and mind us, we are looking at X-ray and gamma ray. So all the interaction we are going to be looking at is actually the interaction of the X-ray or gamma ray with the atom. So Rayleigh scattering is actually a type of scattering that affects the atom as a whole. It affects the atom as a whole. You have dense nucleus. You have electron cloud. You now have a photon coming. But instead of the photon to move and affect the orbital electrons or the innermost electron or even the nucleus, what it does is it just affects, it just interacts with the whole atom, that is with the electron cloud. You know, these electrons here, we have just depicted it as a two-dimensional image. It is actually something three-dimensional in nature. If we have so many electrons in their orbit, so many orbits, orbital electron, this in chemistry, we know the SPD, LFM orbital. They all have, they're all revolving around something in a particular fashion, in a particular, not just straight revolving as we might think. So the electromagnetic, this X-ray or gamma ray, just interacts with the whole proton, I mean with the whole atom. What happens is the atoms becomes excited. The whole atom becomes excited as a whole. The whole atom becomes excited, not the electron, a single electron becoming excited or a component of the nucleus becoming excited. When that happens, this one we want to, of course, and go back to its former state, its former stable state. By that, it just gives off that energy again. It gives off another X-ray. This one enters it, it becomes excited. It has to go back to its former state, an unexcited state. So to do that, it gives off the excess energy it has been acquired. And this energy of this X-ray or this photon and the energy, they are about the same thing. So this Rayleigh scattering at times is called elastic scattering and so on. At times it can even be called elastic. So it's this type of scattering is one in which the photon, incoming photon, affects everything, and it just slightly changes the direction of the scattered photon, the photon that will be eventually emitted by these whole atom, can be at an angle slightly different from what it was before. See, here it is very, very small. So this happens at times in radiology, but it doesn't happen so much. It is usually with low energy X-ray. Low energy X-ray. When you have low energy X-ray, so that that energy is not able to concept excitation of a single electron or ionization. It tends to go with that. And this one is this type of scattering happens with especially mammography. It happens within the mammography range because we are looking at around 15 to 30 kilo. So this rally scattering is a major one in mammography because of the low energy. So when we are looking at the low energy electrons, low energy X-ray, one of the major these things is not major, in substantial amount of scattering will be as a result of Rayleigh scattering. So that is it about this. And we just know that this happens with low energetic X-ray. And for a Thompson scattering, Thompson scattering, which sometimes called inelastic scattering, is the major scattering process, major interaction that happens in the diagnostic and energy range. And very, very annoying. If it were possible for this not to be happening in the diagnostic imaging range, then that would be very, very good for us. But unfortunately, it has to happen because of its nature. Compton scattering has to do with a photon interacting with essentially loosely bound orbital valence electron. Now this electron, valence electron in outside. We have a photon. We have a photon which can be X-ray or gamma ray coming into it, interacts with this, and it then knocks it off. The electron of this one is very, 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 very small. Like told us before, this usually happens with the valence electron, and it is annoyingly a major portion of the interaction that we deal with in the energy range that we use in radiology. So when this knocks it off, the photon energy, the energy of the proton, and the binding energy of the electron, which is very, very small, very, very small, is so we have the photon energy. This photon energy should be equal to the energy of the injected photon of the injected electron. When this happens, this photon energy, the photon will be scattered at an angle. It will be scattered at an angle. It's something that also happens. It will be scattered at an angle. So we have the electron following its own trajectory. We have the photon, which is which will have a reduced energy following its own path. But there are so many things we need to know about this and how can this be scattered, to which angle, to what amount of scattering can this one go? And what's the highest amount of scattering can this one go? What the energy dependence of the incoming photon and the energy that will be imparted to this electron and then to use a gamma ray. I think I have a diagram of this. Let me share the screen of this Compton scan. I hope we are seeing the diagram there.
Yes, sir.
Okay.
Yes, sir.
Thank you very much.
Yes, sir.
Okay. You can see the incident photon coming, essentially interacts with one of these valence electrons. The electron is knocked off, and the electron knocked off is the Compton electron. And then we also have the deflection of a scattered photon, which is at an angle, which can be measured. So the major thing that we have with the Compton scattering is that it is the energy, the choice form of interaction when the photon interacts with electron and atomos and electron. And Compton scattering is a very, very funny interaction in the sense that it's very, very difficult to us to find its relationship with with Z, the proton number. Very different from the photoelectric effect. We can have the electric effect and have a relationship of the electric and probability of the electric effect and happening we can see. But for Compton scattering, it is not straightforward. So the energy of this photon energy is hello.
Hello.
I can hear you.
The board.
Okay, so sorry. So the photon energy is the incoming photon energy. Incident is incident. Photon energy is the same thing as the energy of the electron. Energy of Compton electron or electron plus energy of the scattered photon. Scattered photon. And there's something about this. This one has a particular range of an angle that is can be scattered. This one also have this one also has a particular range of energy angle which can be scattered. Electron, the highest scattering angle is 90 degrees. The photon. That is the highest scattering that this electron can undergo. So you can have scattering, it can be scattered forward in the forward direction. This Compton comes scatter it in the same forward direction along the 0 degrees. But it can also be scattered 1 degree, 2 degree, and so on and so forth. But the highest amount of degree that the electron can be scattered is 90 degrees. You can't have more than that. So that is the limit of the scattering angle that this electron can have. But for the gamma ray, for the scattered gamma ray, we can have what we call back scatter. Gamma rays. Please, could you please mute? I think there's somebody by the name Techno. Could you please mute? Please. Okay, thank you. I think he has muted. So we have this gamma, the eventual gamma ray that will be produced by this interaction can be scattered in all manner of angles. It can be forward scatter, just like an electron can be forward scatter. It can scatter angle 1 degree, 2 degree, and even up to 180 degrees. So you can have a back scatter of the scattered photon, thus becoming, and to have so many energies to play with that. So we have a particular formula, but I don't want to go into all those formulas. So just for us to know that the electron, the maximum angle can be scattered to is 90 degrees. Whereas when the gamma ray, it can be scattered to any angle, even up to 180 degrees. And then the more the number of energy of this photon energy, the lesser the number of energy. This photon energy also affects the amount of energy this one is going to receive and the amount this is going to receive. So the energy discrimination of this photon affects the rest. So that is why this Compton, because of this basket or this scattering whatever, that is why Compton is an issue for when we are doing our imaging. Scattering is a problem for both the patients and then especially the radiographer from the radiologist. So we don't want to stay close to the patient. So the more the amount of radiation the patient is we are using to form the image, the more the scattered electron, the scattered photon are reaching the radiologist and the other people using it. So it is good for us to have this at the back of our mind that it is not only the patient that suffers, the physician, whosoever is using that EM rays, whosoever is using the photon energetic radiation is also receiving, is also at the receiving end, owing to this Compton scattering. So this is what we want to avoid in medical imaging. There's a way we want to reduce this as much as possible. We do that. Unfortunately, it is not. One of the ways we can reduce it is by reducing energy. As you increase the energy, of course, increasing the energy reduces the portion of this. It also reduces the portion of the electric effect. So there's a problem there. So it is just to manage it as much as possible. So we use high Z elements just to remove this Compton scatter. That is why the shields we use in the shield we use in the shields we use in radiology, in radiation medicine. They have high Z material. So those ones can get whatever scatter the photon or electron, the photon that is emanating. And then quickly, with electric effect. This is the most important interactions that we want in radiology. The most important, because we want in radiology. Why? Because this has got nothing to do with photon. We don't have any scattered photon. The whole energy is absorbed by the electron, which is ejected from the nucleus. From the atom. And that happens. This one takes a kind of a different path. For photoelectric effect to take place, the energy, the, the photon has to interact with the inner electrons. I mean, yeah, inner electrons in the shells. Though once or twice, it can have the photoelectric effect such that the photon at the valence will be, I mean, the electron and valence shell can be knocked off. But in most cases, photoelectric effect has to do with this photon interacting with the innermost electron, which is of course tightly bound. For Compton, the outermost electron is loosely bound, but for this tightly bound electron, when it is knocked off, it is knocked off. So many things, the electron, the atom will now be put in a very, very unstable state, very, very much more unstable than the instability that Compton scatter poses. So that one is simply electron from the surrounding tissue taking the place of the one that has been knocked off. But this, so many things happen, which of course we have dealt with the preceding lectures we had. When this one happens, we have the electron moving from here down here. When this one moves away, another one will move from here to here. If you have another shell, something will continue. And this is simply as I say, the atom becomes stable. I'd like to, the time is fast spent. Let me see what we can do about this. I think we'll be able to cannot share this screen effectively before. Almost I don't justice it. I probably think we need to stop here because this photoelectric effect is one of the most important interaction we have to do with radiology, and I wouldn't want us to rush it. At this point in time, I think we can call it a day here and then fix one more lecture to be able to finish this thing because we can't just, like I said before, the 2 lectures per topic or whatever per week might not suffice learning some topics, and this is one of them. And normally this takes at least 4 lectures of 2 hours. But because of the nature of our exam, I mean, because of the time frame of our exam, which is going to come in October, that's why we have to do it this way. So we have to rush, we have to do it as, we have to take this approach. I think we need to fix a lecture, maybe probably on Monday, and see how we can finish this off and then look at our quiz. And some of us just joining today. There was a quiz, a pre-quiz test that, I mean, a pre-lecture quiz that was sent to our emails. It is timed. We I prepared around 38 questions to be answered in 45 minutes. It's just for us to know our understanding, test our understanding of this concept before the lecture. And then at the end of the lecture, the test is also going to be sent to us so that we go through them again and then give our responses. Perhaps we should have increased our knowledge of some of the salient points we weren't able to get before the lecture. So it is going to test our understanding of the length, the depth to which we have gotten, understood the topic. So for those joining today, sorry about that. Maybe when you officially join us, the test can be sent to you. Some people didn't do the test, few, about 2 or 3, around them 3 or so of those in our group didn't do the test. Like I said in the message I sent, it is not a mock exam, it's not anything. The timing I put in there just to make it look like a real exam. That's us, because in all topics we're going to be having both post-test and lecture quiz and the pre-lecture quiz. The 2 quizzes are going to be the same. At the end of the day, for us to know how far we have gone. At this point in time, I want us to call it a day that we complete a photoelectric effects, then effect production, then we go to the radiation units on that next lecture day, and then do the second half of the lecture. We look at we go, okay, okay, yeah. I thought the next, if my class may be an hour, so then we wrap up. I will wrap up with the quiz proper. We now go through all the quiz and questions, and then from there we can then also get some insight into some points and that we are not raised because one of the importance of quizzes is just because it's going to lead us to other aspects that we maybe didn't inadvertently um, not talk about. But they're going to help us out a little bit. And of course, those questions, so many questions we are going to come up with when the exam eventually comes. Um, we are not going to have so much exam inertia. So that is it from my end. I would like you to invite other people who are writing. There are others who wouldn't even be writing this October that might be writing next year, March or April or so, that want to be involved. Because the number of times we go through all this lecture, it doesn't matter if we've had this lecture before or whatever. The more the number of lectures, the more the number of revision, the better the comprehension and the retention. So from my end, I want to thank you all for joining. And we continue our discussion on our WhatsApp page. Thank you. I don't know if any person has any question to ask. So, okay.
Thank you. No
Okay.
question.
You're welcome. I'm signing out. Bye-bye. Thank
you for the class.
You're welcome. Maybe we'll have a lecture on Monday and
Sir.
see how it goes. Okay. Bye-bye.
Thank you, sir.
Time, please.
We will go to our group and then discuss again. We go to
Some of us are not in the group.
Sir, some of us are not in the group.
You can chat me up and see how to, because the group is meant for those who have actually indicated interest and who have, of course, who know the terms of operation. So just contact me through the WhatsApp, through the message I sent you, or through any means. You can contact me through your friend that gave you the link or whatever. Anyway, they have my contact. They have my email address. They have my WhatsApp number, my other number. I used to contact me. So, but I think let me just give for those who want to contact me directly. Okay. I want to contact me. My number is just 0. Can you just give me this? This is not my WhatsApp number. My WhatsApp, I can't. I don't have it offhand. Can you give me text or mail on this? And my WhatsApp, I can't come to. I don't know it offhand. You can send me a text. Text or call with this number. Then from there, I give you my WhatsApp number, and every other thing will follow. So once again, thank you very much, and do have
Thank you so much.
a wonderful weekend. Bye-bye.
Thanks, sir.
Thanks, sir.
Okay. Bye-bye.